Welcome to this video where I'm going to have a look at some recent research that has been done that used micrometeor impacts on Saturn's rings to constrain their age. Now there's been quite a lot of confusion on how old Saturn's rings actually are because they probably didn't form with Saturn and they might be quite young, but you can use micrometeor impacts to constrain pretty much how old they are. So we're going to have a look at that. But before we do, we need to understand a little bit more about Saturn's rings and why you can then use micrometeor impacts to figure out how old they actually are. So Saturn's rings are made of lots of icy particles. So it's not a solid ring. There's lots of individual particles. Think of them as lots of small moons. They all orbit in the same sort of direction and they go around Saturn. And actually, it's quite thin. So Saturn's rings are on the order of meters thick, when actually width-wise and radius-wise they can be hundreds of thousands of kilometers. So they're very, very thin in comparison to how big they actually are. So lots of small particles like moons all moving individually around Saturn. They all go in the same direction, so they're all orbiting in the same direction, and it's like traffic on a road, I suppose, with lots and lots of lanes. They're all going around in the same sort of direction. The ones closest to Saturn are orbiting faster because of the gravitational force from Saturn, meaning they have to travel faster to stop them falling inwards. Now, the planets are about 4.5 billion years old. They sort of formed together, and Saturn stands out amongst those as having significant rings, whereas the others don't. So you've got an image of Jupiter down there on the lower right, and it's got a very thin, tenuous ring. Now, Uranus and Neptune also have very thin rings, but Saturn is the only one that has a large, significant ring system that you can actually see from your own back garden. The others, you won't be able to see them without much more specialist equipment or larger equipment or even spacecraft that go nearby. Now, there are some asteroids that have these rings as well, but again, they're very, very thin. So Saturn is very unique in that it has a very large ring system compared to all of the other planets. Now, what does that really mean? Well, it means it likely didn't form with Saturn 4.5 billion years ago. And the reason for that is planetary rings are very short-lived in astronomical terms. So in about 100 million years' time, Saturn's rings will start to be depleted and they will decrease and be a lot less significant than they are now. So they don't live very long. So the fact that they have them now is interesting. It means they likely formed more recently than the planet itself, but we don't really know exactly when they formed. So the reason why the ring would actually be depleted is that the inner part of the ring, so the ring closest to Saturn, flows onto the planet. So it actually falls onto the planet grows a little bit in size, and the ring gets depleted. Now the reason why it does that is because all of those particles are orbiting around in the ring, and they occasionally bump into each other. Now when they bump into each other, they actually change their trajectory. So it means they have some radial movement then in their movement, which means they go inwards or they go outwards. And it causes a spreading. We will call this like a viscous spreading. So you think of a viscous fluid and it would spread. Well, the same thing happens with Saturn's rings. It will spread and the inner part of the ring will fall onto the planet and the outer part will move further out. But this has been calculated to be on the order of tons per second that is then falling onto Saturn. So it's not necessarily a small amount. So a reasonable amount of material is falling onto Saturn every second. The outer part of the ring, it goes beyond something known as the Roche limit. And once that happens, the gravitational force from Saturn reduces where those particles can gravitationally attract each other. So as the ring spreads outwards, it actually forms moons. So not only is part of the ring falling onto Saturn, the outer part then creates new moons, which, an example here, they then drift outwards and you get the sort of structure that we get around Saturn. So those two things will deplete the ring relatively quickly. So again, Saturn's rings are quite unique. Other planets don't have them in quite significant as Saturn does. So when you actually look at the composition of Saturn's rings, you can measure that. So Cassini was measuring the composition as it was orbiting there, and they're about 98 to 99% water ice. So those little particles or big particles orbiting around in this ring, they're predominantly water ice. But there is a very small percentage, so 0.1 to 2% is non-icy material, which is a pollution from micrometeors. So when these little objects hit the Saturn's rings, they will contribute a pollution to that. So if Saturn's rings were completely water ice when they first formed, over time you get more and more pollution from these micrometeors. And what you can then do, if you calculate the ratio of that polluting material to the water ice, you can calculate how long they've been exposed to those sort of impacts. And this is what was done with Cassini's cosmic dust analyzer. It measured the micrometeor flux, so you can get a rough idea how much is actually hitting the rings over time. So it's about 10 to the 17, 10 to the 16 kilograms per square meter per second. So it's not a huge amount, but it is something nonetheless. And that was measured by Cassini, which was orbiting the planet. So if you know how much is actually impacting the rings over time, you can measure what the concentration of that is now, and then you can rewind backwards to when you get to predominantly water ice in the ring. And when that was done, it was found to be about 100 to 400 million years old, which backs up other work that use a different method to get a similar sort of age. So by using the pollution in the rings from micrometeors, you can then calculate the ring exposure time, because you know how the rate of impacts. That then gives you your time, or when they likely formed, which is 100 to 400 million years ago. So thank you for watching, and if you enjoy, then check out some of the other videos.